Okay, so a 6-cylinder 4-stroke diesel engine of bore 750 millimeters and stroke 1000 millimeters has a brake output of 110 kilowatts at 3500 revs per minute. The volumetric efficiency is 80% and the operating condition referred to as the ambient condition of 1.013 bar and 20 degrees Celsius, and Cp is equal to 1.055. The engine is now fitted with a mechanically driven supercharger. Which version has an isentropic efficiency of 0.7 and a pressure ratio of 1.6? The supercharged version of the volumetric efficiency of 100. The supercharged version has a volumetric efficiency of 100%, referred to as the supercharger delivery pressure and temperature. If the indicated mean effective pressure is 0.25 bar during the supercharging, calculate the indicated power and the net increase in the brake power to be expected from the supercharged engine. Take the mechanical efficiency of the engine as 80% in both cases and the mechanical efficiency of the drive from the engine to the supercharger as 95%. Okay, so I'm going to break down how to analyze the question first. Okay, so the engine has a 6-cylinder 4-stroke diesel engine of bore 750 millimeters and stroke 1000 millimeters. So we know that its number of cylinders is 6. It's a 4-stroke engine, therefore our K is half. The bore is 750 millimeters, converting to meters is 0.75 meters. Our length is equal to 1000 millimeters, that is converting to meters, 0.1 meter. Now the engine has a brake power output of 110 kilowatts at an engine speed of 3500 revs per minute. So we have the brake power output at 110 kilowatts and the engine speed is 3500 revs per minute. Converting revs per minute to revs per second, that is dividing by 60 to give you 58.3 revs per second. Now the volumetric efficiency is 80% at this operating condition, referred to as ambient conditions. So at ambient conditions, we have that the volumetric efficiency is 0.8, 80%, that is 80%, 0.8, has a pressure of 1.013 bar, that is, the pressure is equal to 1.013 bar. If you convert the bar to kilopascals, it's 101.3 kilopascals, and 20 degrees Celsius. So we know that the temperature at ambient conditions is 20 degrees Celsius. Converted to Kelvin, that is 293 Kelvin. Has a specific heat of 1.005. Now the engine is now fitted with a mechanically driven supercharger, which version has an isentropic efficiency of 0.5. So once the engine is fitted with a mechanically driven supercharger, so we're now at supercharged conditions, the isentropic efficiency of the compressor, isentropic efficiency here, because the supercharger is going to be around the compressor area, so let's say the isentropic efficiency they're talking about is going to be relating to the compressor. So the isentropic efficiency of the supercharger is 0.7, has a pressure ratio of 1.6. Now pressure ratio simply means P2 over P1. Pressure ratio is P2 over P1, so P2 over P1 is equal to 1.6. The supercharged version has a volumetric efficiency of 100%. 100% is 1. 100% is equal to 1, referred to as the supercharged delivery pressure and temperature. If the indicated mean effective pressure is 0.25 bar, pressure, the indicated mean effective pressure is 0.25 bar. Converting to pascals, in kilopascal, that is times 100, that is 25 kilopascals. Now, they said calculate the indicated power and also calculate the net increase in the brake power to be expected from the supercharged engine. Take the mechanical efficiency of the engine to be 80% in both cases. Therefore, both at ambient condition and at supercharged condition, the mechanical efficiency is 0.8. Then the mechanical efficiency from the drive from the engine to the supercharger is 95. So the mechanical efficiency of the supercharger here is 0.95, 95%. Okay, so the first thing we are asked to look for is our indicated power. So we're going to look for the indicated power at both the ambient conditions and the supercharged condition. So let's start with that. Now, so let's start. At ambient conditions, we will say, recall, since we were given our mechanical efficiency and we were also given our mechanical efficiency at ambient conditions, and we were also given our brake power. Mind you, these first parameters are just the general parameters for the engine. These are the general parameters for the engine. These are what we're working with at normal, at ambient conditions also. So this brake power here is the brake power at ambient condition. Okay, so we can now say, recall that mechanical efficiency is equal to brake power over indicated power. We're looking for the indicated power at ambient conditions. We already have our brake power, we already have our mechanical efficiency. So making indicated power, so the formula is indicated power is equal to the brake power over your mechanical efficiency. Brake power was given as 110, mechanical efficiency is 0.8 to give you 137.5 kilowatts. Now, at supercharged conditions, we were given our PI at supercharged conditions, which is 25 kilopascals. We have our parameters for the engine, the general parameters for the engine, which is SK, our planks, that is L. We have the diameter to find A, we have our engine speed, we have our K, we have our S. So we can as well say that at supercharged condition, indicated power is equal to P lengths. We have your PI, your L, your D to use and find your A, that is pi d square over 4. Your engine speed, which is 58.3, times your K, which is half, times cylinder, which is 6. All will give you 193.2 kilowatts. So we have our indicated power for both the ambient condition and the supercharged condition. Pardon me if my hand is shaking, I'm very tired right now. So what we are asked to find next is the net increase in the brake power expected from the supercharged engine. So what we're going to look for is the increase in power from the normal brake power to the supercharged brake power. So what we are going to do right now to find brake power in the compressor, we're going to recall that okay, your brake power is equal to your, okay, we can say that brake power is, you can get your brake power from your indicated power. Removing your losses from your indicated power will give you your brake power. So we are first going to find our power input in the supercharger. The power input into the supercharger, now we're going to subtract that by we're going to subtract that from our indicated power that we got in the supercharged condition, which is this. So the power input in the supercharger is given by this formula. WC, that is working compressor, is equal to MA times CP times T times the pressure ratio times your gamma, pressure ratio raised to the power gamma minus 1 over gamma minus 1 all over your isentropic compression. We have our pressure ratio, we have our gamma, we have our T1, we have our CP, we don't have our mass of air. So this is what we're going to look for now. So let's say mass of air is equal to density of air times the volume of air. This can still be further written as the pressure of air. We can replace density and say the pressure of air over the gas constant of air times the temperature of air times our VA. We have our pressure of air, we have our gas constant of air, we have our temperature of air. We don't have VA. But volumetric efficiency at supercharged condition was given, that is 100% 1. So we can now say that volumetric efficiency is equal to VA over Vs. Making VA subject to formula, we have VA is equal to Vs times the volumetric efficiency, where we know that the Vs, or your swept volume, is equal to lengths. So we simply do our lengths here, length times the area times the engine speed times your K times your S, to give you 7.7 meter cube per second. So we'll say VA is equal to your volumetric efficiency times your Vs. Volumetric efficiency at supercharged condition is 1. Your Vs was gotten as 7.7, so your VA is also going to be 7.7 meter cube per second. Now we can put this into our formula for M. So M is equal to pressure of A over gas constant A, temperature A, times your VA. Your pressure of air was given in the parameters. Gas constant was given, even if it was not given, gas constant is supposed to be 0.287 times your temperature of air, which was also given, times the volume you got. It will now give you 9.278. Now, this part is kind of tricky because what you're getting here is supposed to be in kilograms per second. But for some reason in the textbook, they chose to leave the answer in kilogram per minute, which is actually not correct. But I don't have a reason to argue with them at this point because I've tried different variations. It doesn't work out. So I just have to leave this answer in kilogram per minute for now. Just leave it like that for now. I just want to show you how exactly to solve a turbocharger question. We will get back to this later. So for it to be in kilogram per minute, we're going to use, all our solvings is kilogram per second, so we're dividing again by 60. So divide your answer here by 60, you have 0.155 kilogram per second. So we can now go again and say, recall the power output into the supercharger is minus WC is equal to MA. We now have our MA, we have our CP, we have our T1, our pressure ratio, gamma, we have a value for gamma, we have our isentropic compression. But now, since there is a drive from the engine to the supercharger, the equation becomes minus WC is equal to MACP, your T1, open bracket, your pressure ratio, gamma minus raised to the power gamma minus 1 over gamma minus 1, all over isentropic compression times the isentropic or the mechanical efficiency of the supercharger. So we put all our parameters inside. When we solve, we're going to get our power input into the supercharger, which is 9.84 kilowatts, and this is a loss. You can see the minus here, the minus in the compressor, to show that this is a loss. So what we're going to do is recall this formula that I gave, that your mechanical losses are equal to your indicated power minus, your indicated power minus your brake power. This can also be written as your brake power is equal to your indicated power minus your mechanical losses. So like I said before, this is a loss, so what we're going to do to get our brake power is equal to indicated power minus that loss we got. So that is the indicated power at supercharging conditions we got minus the loss at supercharging, to give you 182.65 kilowatts. And now the question asks for the net increase in power, in brake power. So what we're going to do is the brake power at supercharged condition minus the brake power at ambient conditions, that is natural conditions, that is this minus your natural brake power, to give you 72.65 kilowatts, and that is your final answer.